I'll come over and do it. 8 o'clock. Good. Sound good? Morning, everyone. Welcome back to the last day of the first week of Chem 1A. We've already charged through just a ton of stuff, and we already have midterm coming up a week from Tuesday. July 4th holiday is, we take Monday off, and then Tuesday evening, 6:30, is the first midterm exam already. So let's pick up where we left off last time. We were talking about, we can talk just a quick review. We were talking about thermodynamics, and we talked about work, heat, energy, and the transfer of energy by work and heat to two different systems. One was charged particles, where we found you could go to high potential energy by pulling the charged particles apart. So you put energy in because they're attracted. So the energy you're putting in goes into the system, which is the two charges. So higher potential energy when you pulled them apart. We found you could add heat, and that would start the particles moving more random motions and kinetic energy. And we looked at gases being compressed in a cylinder under a variety of conditions, isothermal conditions where the initial and final temperature are the same. And we defined a state function which only depends on the initial and final state. Work and heat are not state functions, but temperature, volume, pressure, energy, anything that just depends on what the state is when you just look at it is a state function. I've always thought it was a kind of a highfalutin name, state function. It's like, yeah, it's like a presidential, you expect them to have a motorcade. Oh, look, it's a state function. Maybe there'll be a parade. But all it means really is final minus initial will always be the change, and the path between doesn't matter. It matters for work and heat, but not the state functions. So we are going to do a chem quiz, and we were hoping you would have a rubber band this morning. Where is mine? Oh, who? I'll find mine in a second. First, I'll ask you the question, and then I'll find, oops, this isn't even it. Sorry, we have to advance to here. There it is. A stretched rubber band is suddenly released. What happens to the temperature of the rubber band? So stretched rubber band is released. What happens to the temperature after it is released? So think about that for a second. Talk about it amongst your groups. You can try the experiment. I'm going to do it with you in a minute and see if you can come up with a solution. Hey, you've had some time to discuss that. We have some of your colleagues here join. Sound. Do I have sound back? Am I live? Yes. So we have some of your colleagues right here in the classroom today, so I can chat with them. You're welcome to join if you can find a day that works. Let's see what you were thinking about this. So equally, I don't know if you can see that, but absolutely equally split between increases and decreases. Not unexpected. Let's do the experiment. So you have to do it with me. And the fatter your rubber band, the better. Let me see a Zoom room. Do you have a Zoom room open? So there's people who are in a Zoom room with Sydney right now. Do any of you guys have rubber bands? Tell me one person has a rubber band. Anyone? Oh, come on. One person has a rubber band. Would you mind one person who has a rubber band if we put you up here so I can do it with you? Yeah. No, I'll bring your display over here. She can hear that, right? Or he? How do you feel about that? Join us in the classroom, will you? She declines. Okay, that's completely fine. And we only have one rubber band here because we're also lame. So I'll do it. Otherwise, we would have our colleagues here stand up and do it. So do it with me. Those of you that have a rubber band, here's what you're going to do, and do it later on your own. The thing is, you can get the answer if you do this. So stretch the rubber band. It says a stretched rubber band is released. So stretch it and hold it. Okay, hold. Now what I want you to do is release it, then touch it to your bottom lip. Touch it to your bottom lip now to practice. Get an idea what the temperature is. Okay, then release it and touch it to your bottom lip. What do you notice? It's actually quite dramatic. It should be quite a bit cooler than when you first touched it after the stretch. And why is that? Well, stretching it, our energy of stretching added energy. It increased the energy of this rubber band. Then we waited, so it would become isothermal. If you wait, the heat that we put in, the energy that we put in, dissipates. Then we're going to rapidly, adiabatically almost, adiabatically is the best way to say it, adiabatically release it. So do an adiabatic process where this rubber band does work on my hands and pulls them back together. So the system doing work, and it does it adiabatically fast, it has to use some of its energy, and its temperature goes down as a result. Boom. Cool rubber band. All right, awesome. Let's just take a poll quickly because I'm interested. The poll is, how many people had a rubber band? A, you had a rubber band. B, you had no rubber band. I'm just interested to know. Let's get some responses there. Have a click, push a button quick. We'll get a 60 or 80 views so we have a good sample of the class. And let's just see. A, you had a rubber band. B, you didn't. Is that what I said? Oh my goodness, a lot of people, over half of you had a rubber band. I'm sorry we couldn't find somebody to join us in the classroom. So I hope those of you that had the rubber band could feel that cooling. It's the dramatic and kind of unexpected result of thermodynamics. So yes, it's an adiabatic process. So the system does work. So its temperature decreases. So we're not going to do any of that math. We are going to intuit it and figure out that decreased. Okay, so we will continue and talk about heat flow now. So we can talk about energy and temperature changes in terms of measuring the heat flow, and it turns out it's relatively simple to do because we've seen if heat flows, it's often related directly to a temperature change in the sample. For an ideal gas, it's absolutely reflective of that. Ideal gases, the only energy they have is kinetic. So if you add some energy via heat or work, the temperature changes. So heat capacity is how we talk about how heat is transferred. All substances absorb heat in different ways. Some absorb heat and their temperature changes rapidly. So you absorb a joule and your temperature changes 10 degrees. Some, you absorb a joule of heat and your temperature only changes half a degree. That relationship between the amount of heat you absorb and how far the temperature changes is called the heat capacity. And it's really a capacity in the sense that you could think about it as two flasks. Here's two flasks, and these have different capacities, don't they? This has a high capacity, this has a low capacity. And if you were to pour water into them, the same amount of water in the two flasks would bring the level of the water to a different height. Because this one, keep touching the screen with my, and now it won't go backwards. I keep touching the screen with my sleeve. I don't even know where I went. Stand by. This one, the same amount of water. So the same amount of heat raises the height less because this has a higher capacity. It can absorb more energy per change in temperature. So pouring a fluid into a flask, is that analogous to an energy change? Absolutely. And if I'm pouring it into the flask, is that analogous to exothermic or endothermic, or is there no relation? We'll just go through this one together because we've talked through it. You pour into a flask and the height raises, that's analogous to adding energy and the temperature raising. So adding energy, we've talked about that. We call that an endothermic process. So heat capacity is really a volumetric capacity analogy that we can use to understand what's going on. So if I add heat, my Q heat is greater than 0. The height is analogous to the temperature change, and the volume change, total volume change, is analogous to the energy change. The volume of the liquid in each would be the same. It's the height that's different. So that's a straightforward analogy. In order to get this to change by the same height, we have to add a lot more liquid. It has a much higher heat capacity. So we can measure the heat entered. Now, here's an important part because we've been talking about this heat, but how do you measure it? It's kind of an amorphous concept. You put a flame under your beaker or your pot on the stove. Heat is entering, but how much? Heat's going all over the room, really, because the flame is hot. How much of it is going into your sample? Well, this gives us the ability to measure it. We know the temperature change per joule added. So all we have to do is measure the temperature change, multiply by this heat capacity and the amount of stuff there, and we can see how much heat entered the system. So this is an experimental way to get that quantity Q. The quantity W, the work, sometimes we could get that because it's pressure times the change in volume for a gas. And we can measure both of those things externally. Change in volume is obvious, but we know how much external pressure we had. That work we can measure. Heat is a little more mysterious, but here's our way to get the heat measured in the system as well. So here are some heats. They're often listed in different ways. The specific heat capacity, which goes by mass, joules per gram Kelvin. The molar heat capacity, which goes as a mole per Kelvin. So how many joules does it take to change a mole by 1 degree Kelvin? And degrees Kelvin and degrees Celsius are the same size. So degrees Kelvin or degrees Celsius change is the same. So here are some various compounds. Kind of interesting that if you go by the molar heat capacity, most metals have about the same heat capacity. And we kind of can understand that a little bit already. We've looked at solids, and solids are packed and regular. And you would expect, well, they're packed and regular. They're all metals. They have very similar properties to start with. The packed structure reacts to heat in a similar way per molecule, per atom, per mole. Okay, by mass, they would have different heat capacities, but by the number of particles, they're very similar in heat capacity. So we get this understanding that heat capacity does depend on the motion of particles, and if all the particles are kind of the same, and the same kind of interactions like in different solid metals, then the heat capacities are the same. But there's widely varying heat capacities for different substances. So water we deal with a lot. Its heat capacity, it takes 4 joules to raise the temperature of water 1 gram by 1 degree. It takes 75 joules per mole, and we know per mole this number times 18. There's 18 grams per mole. And that's for liquid water. If you did solid water, it's different. And that should make sense to you as well, because the heat is going into the kinetic motion of the particles. And in the solid phase, they're rigid and they have strong intermolecular forces. You go to the liquid phase and those are relaxed, and it's easier to absorb heat in general. You can see for water, it's very interesting and unique that the heat capacity increases. And here are some other liquids. So this is ethanol, and this is chloroform, or carbon tetrachloride. And you can see the very low heat capacity for carbon tetrachloride, the slightly higher for ethanol. And we're going to learn how to kind of gauge and predict what these are. You might already anticipate in advance, it has to do with the potential energies when you're talking about condensed phases. There's more potential energy, there's stronger interactions between the methanol and the water than the chloroform. So let's talk about that. Let's try to do a calculation. In general, we don't, the chem quizzes are not too calculational. And again, this is not super calculational. You just have to think, what's the relative temperature change? Just the magnitude of the temperature change. So don't worry about the sign of the temperature change, just the absolute value of the temperature change when a kilogram of hot molybdenum, molar mass 95, is dropped into a kilogram of cool water. Okay, I'm going to give you a hint. The mass should be kind of easy because a kilogram, this is 95 grams per mole, a kilogram, 1,000 grams. So you can see that this is just a few tenths of a mole. So that should make some of the mass easy. And the molar heat capacities of metals are all around 25. I'll start the quiz. So this is captured, and I'll bring up that table here. But if you've downloaded the handout, you have that table in front of you. Think about that for a second, and we'll take a vote. Okay, let's take another minute or so. You guys are chatting about this. You might be scratching out calculations. Okay, guys, let's see what you're thinking about this one. Push a button if you haven't so far. And I'll see what you're thinking. Many of us think the metal, so around 60% of us think the magnitude of the metal temperature change is bigger than the water temperature change. I agree with those. That's the conclusion that Helen and David, who are here with us, came to. So why is that? Well, you can think through this relatively in a relatively straightforward way. One, you would conserve energy. All of the joules of heat that leave the metal enter the water, so the heat absorbed by the metal, or the heat released by the metal, is the heat absorbed by the water. And then you can kind of talk it through. We had 95, about 100 grams of molybdenum. Excuse me, we had, did I say a kilogram of both? What was the, yeah, I think I said a kilogram. A kilogram of each metal. So a kilogram, we did backwards, a kilogram is about 10 moles of molybdenum. And we had water, a kilogram of that's a mole of water is 20 grams. So that's 500 moles. So you have many more moles of water than you do of the metal. And water, the molar heat capacity was 75 joules to change it by 1 degree. The metal changes by 1 degree at about 25 joules per mole. So the metal has this small heat capacity, and the water system has this ginormous heat capacity. So every joule that leaves the metal changes the metal by a certain temperature. Every 25, let's do it that way. Every 25 joules that leaves changes that by 1 degree. But those 25 joules that leave don't change the water system as much, because the water has a high effective heat capacity, lots of ability to absorb heat. So the metal changes relatively fast in temperature, and the water changes slowly in temperature. So we can get there kind of thinking it through. You could also just do the math. So the heat capacity of the metal, the heat capacity of the water. We have, if we use their mass heat capacities, we don't even have to put the mass in there because they were both a kilogram, both 1,000 grams. So the temperature change is the ratio of the ratio of the temperature change is the ratio of the heat capacities. So the temperature change of the metal over the water is the heat capacity of the water over the metal. This is a big number. That's a smaller number. This ratio is greater than 1. The temperature change of the metal is greater than the temperature change of the water. Great. Looks like I did the math about a factor of 16. Okay. I'll talk this one through with you. This my mother used to say to me. That's why I wrote this chem quiz. I didn't understand it when I was a kid, but my mom, who is not a scientist, my mom was a homemaker. We were baking together one day, and we were making banana bread. And we had 2 loaves, enough batter for 2 loaves, and I wanted to just throw them both in the oven and bake them. And my mom said, "You can't do that. That'll overload the oven." And I said, "No, they both fit. Both pans fit in there." But my mom, from experience, knew that if you put those 2 masses in your oven, then the heat from the oven can only be delivered at a certain rate. Your ovens are rated. So you'll see ratings like you have a 3,500 watt oven. A watt is a joule per second. So that's how fast the oven can deliver heat to your banana bread. But if you put 2 banana breads in there, it still can only deliver that heat. So over the same amount of time, only half the amount of heat goes into each banana bread. So what she meant, it was a thermal overload of the oven, not a capacity overload of the oven. So this unit is a unit of power, watts. Joules per second, how much energy per second leaves. Something that's very powerful delivers a lot of joules per second. You should be thinking back to that one of those first chem quizzes we did with the exploding balloons. You said to yourself, the one that had the ginormous explosion released less energy than the hydrogen balloon. Why was that? Well, we can already kind of understand why. Energy is an extensive property. It depends on how much you have. You had more hydrogen, more fuel, a full mole in one balloon. The mixture, hydrogen-oxygen, had half a mole of hydrogen to burn. So the full mole released more energy. But since it was mixed in the other balloon, the reaction could happen fast. The balloon that we had to pop, the oxygen had to mix from the room to make the explosion go, relatively slow. So it released its joules in more seconds. And even though there were more joules to release, the explosion of the other balloon, half the amount of energy, but many times more the speed, is what gave you that concussive explosion. So those of you that are interested in explosives or explosions should be aware of that. It doesn't matter how much energy you can release. It matters how fast you can release it. The power, not the energy, is what makes the boom. So this one, 2 cakes in the same oven. You're delivering heat at the same rate. So you'd fill up in a certain time, you'd bake 1 cake, but if you bake 2 cakes, then you have to split the flow of heat. And again, we use this water analogy, and they get to half the temperature in the same amount of time. So they do not bake. You don't get the full cake to 325 degrees. And if you're on the Great British Baking Show. Anybody? Great British Baking Show? Ooh, oh my goodness. Many people in the room watch the Great British Baking Show. So that means Paul Holly would come up and say, well, your doughs are quite stodgy. Overloaded your oven. Oh, I love the applications of science. So we can measure heat flows carefully. So we need to set up a system where we can measure the heat flow. So what we need is a system where we can carefully measure temperature changes and the heat doesn't go anywhere else. So we need to isolate a system so all the heat leaving our system goes somewhere we can measure. And we do that in a calorimeter. So we do a reaction and we surround it with things that we know the heat capacity of. So we can calculate, okay, the heat's going out, and I can measure the temperature change of the, mostly the water in the calorimeter. So this is water, it's thermometer. Here's a little flask to do our reaction in. The whole thing insulated so we don't lose any heat elsewhere. And then you can measure the temperature change of the water, and you can do the calculation we just did with the metal. The heat leaving the reaction goes to the water. So every joule that heated the water came from the reaction. So you can determine the heat flowing from a chemical reaction. A relatively straightforward concept. It employs the first law of thermodynamics. The energy leaving the system enters the surroundings. And we take advantage of that by saying, well, no work is being done, so it's the heat that flows. And I measure the heat, I measure the energy with the heat capacity. So we've been talking about this already. The heat capacity comes from a couple things: the kinetic motion of the particles, so water rotating and translating, moving around. So the more motion, so we get some kinetic components of the energy, kinetic components of the heat capacity. Some of the heat I absorb goes to moving the particles. Here's carbon dioxide, a different example. That carbon dioxide is very good at absorbing heat. It's very good at absorbing radiation from the sun, and it absorbs it and radiates it as heat, and it's warming our atmosphere. So there's thermodynamics happening in the atmosphere. Energy from the sun trapped in these carbon dioxide molecules, and then those carbon dioxide molecules releasing it to the atmosphere, and our atmosphere warming. You could also have that heat energy absorbed as work. So the interactions between the molecules. So they have intermolecular forces. So that's attractions. To move those apart is a work. So, and this is why water has such a high heat capacity, because it turns out, and we're going to study this in a lot of detail, the intermolecular forces in water are quite high. And that makes it have a high heat capacity, because it takes a lot of energy to interrupt the interactions between the individual molecules. And if you have to actually boil them, separate them entirely, go to the gas phase, that takes a tremendous amount of energy. So intermolecular forces, and these molecules here have less intermolecular forces, but you could also have, not in this example, but you could have heat evolving or being absorbed because a reaction occurs. And reactions we're going to classify as potential energy, because it's changing the bonds. It's breaking some bonds, forming other bonds. So there's a potential energy interaction. And here I'm burning methane in oxygen. We looked at that already, to form carbon dioxide and water. Rearranging the bonds, making new bonds, breaking old bonds, is a potential energy change. So those are the origins of how these energies are being transferred and stored in our various chemical and physical properties. So now we can quantify some of these things. So the enthalpy of fusion, the enthalpy of vaporization of water I have here. These are the potential, the strong potential energies. Enthalpy is what I have to do. We were just saying that if we're going to vaporize water, we have to separate all the molecules. That's a potential energy. They're attracted. Oh, I put energy in to make them separate. The enthalpy of vaporization per mole of water. Oh, yeah, I was looking from here and it looked like 4. And I said, no, that's not 4. 40 joules per mole, kilojoules per mole Kelvin. The kinetic energy, this is just a heat capacity. We saw that already per mole, 75 for the liquid water. So we have to add 75 joules to a mole of water to change the temperature 1 degree. We have to add 40.7 kilojoules to vaporize. So what's the relationship here? Let's talk about this for a minute. Which represents the greatest amount of energy per mole? Water solid at -10 going to water liquid at 10. Water liquid at 0 degrees going to water at 100 degrees. So that's what you do on the stove. And bringing water to boiling point. Water liquid at 100 degrees going to water gas at 101 degrees. So think about that, and we'll take a vote. I used to do chemical. Hey guys, if you haven't pushed a button yet, go ahead and push a button and we'll see what you're thinking as a group. All right, that's most of you. Let's see what you're thinking. There's no real consensus actually. C has a few more people, but A and B are also popular. So let's talk through it, and I'll give you my thinking. So again, we could do the math. We have liquid or solid water at -10 going to liquid water at 10. So I guess I would assume that you know, well, number one, I wrote solid and liquid, but the water would melt in there somewhere. So there's both a kinetic energy change. You heat up the solid, then you do a huge potential energy change because you go to the liquid, and then you continue to raise the temperature of the liquid. So the enthalpy of fusion, the melting, is around 6 kilojoules to do that. The little bit on the end, to raise liquid water, it's to raise the temperature of liquid water, it's only 75 joules per mole. This is already kilojoules. So doing that extra 10 degrees of warming of the water is just 75 joules times 10, just a 750 joules, where you're already up to 6,000 joules to do that. So the temperature changes, the kinetic parts don't matter anywhere near the potential parts. And here, you're simply changing the temperature. You're bringing water from 0 degrees to 100 degrees. So that's all kinetic. So if it's a mole of water, 100-degree temperature change, 7.5 kilojoules, those are pretty close. The last one, you're only changing the whole system by a degree, but you have to vaporize. You went from liquid water to steam at 100 degrees. This one's almost all potential energy because you only change the gas by a degree. But that, from the table, 40 kilojoules per mole just to do that. So you can see these phase changes, these potential parts are very much bigger, an order of magnitude bigger than the kinetic parts. And this takes a tremendous amount of energy to do that boiling process. So we'll look at the boiling process, this whole process, carefully. So we're going to plot the temperature change here versus the amount of energy in kilojoules that I apply to the system for a mole of water. So we'll start with a mole of water at ice, and these are the Kelvin temperatures. So the Kelvin scale is 273 degrees different than the Celsius scale. So 273 Kelvin is 100 Celsius, and that's where the water boils. And here we're going to start at 273 or 0 Celsius. Here we have cold ice at 30 degrees below the 0 Celsius freezing point. So we'll start with ice here. And first we have to warm the ice to its melting point. So that takes a amount of energy that's kinetic, the heat capacity times the temperature change for that solid. That's a kinetic component. Then we melt the solid. And we saw that takes these 6 kilojoules. To do that, very much more energy. That is isothermal, the phase change. As the water melts, every joule that goes in, it's one of the mysteries of science, every joule that goes into potential energy for a while, changing the phase, and the temperature doesn't change. So these phase changes are kind of beautiful in that they segregate the kinetic and potential energy into different batches. So here's your isothermal phase change, and we saw that took about 6 kilojoules to do. Now you're at the liquid, so the next joule starts to raise the temperature of the liquid, and that's a kinetic effect. And we bring it up to the boiling point, and we can do an MCP delta T constant calculation here. We can do it in our head. We saw it already around 7.5 kilojoules, 100 or 1,000 grams, we're doing a mole. 1 mole of water by 100 degrees, 75 kilojoules per mole times 100, 7.5 kilojoules to do that process. And kinetic change. And then the steam we have to boil. So here we have liquid water at 100 degrees. To go to gaseous water at 100 degrees, then we have to add that extra potential energy, and that's the big 40 kilojoules per mole to make that go. And I even had to put a little break in the graph because we had to go from 15 out to 55 total kilojoules added. So it's the phase changes, it's the potential that make this big change in our energies. Work, heat, work, potential, heat, kinetic. So heat going in but transferred to work in the system, heat coming from the surroundings transferred to work in the system, still goes into the energy of the system. Temperature didn't change. It's lovely. Okay. So we'll talk about this whole thermodynamic thing now applied specifically to chemical reactions, because that's what we're most interested in. Let's take a look back here. Remember, we said this is what we're going to try to accomplish. Explain everything about this picture. And we've already explained quite a bit about these amounts of material that it takes to do this, and learned that we can take the amounts, the relative masses, and by taking relative masses, we can ensure the right number of particles are there. We can calculate what happens with their relative masses because we can use these balanced chemical equations to see how many molecules react with other molecules. We've talked a little bit about the phases those molecules can be in, gas phase, liquid phase. We've talked about now the energetics of these reactions a bit, and now we're going to continue with that. We're going to focus specifically now on the energetics of the reaction. We're going to talk about, now that we know that this is an enthalpy change, we're going to talk about an enthalpy change formally for chemical reactions. We've been doing it for these physical processes. Now we're going to talk about it in chemical reactions. It's very straightforward. I'll just recast what we've done already, systems and surroundings, in terms of a chemical reaction. So the initial state of the system will be the reactants, and the final state of the system will be the products. Okay? So this could be, at this stage, this could be reactants and products. So an energy change is final minus initial, energy of the products minus the energies of the reactants. So let's say this system, there was an energy increase. The products were higher energy than the reactants. That's different than the hill picture I had. I had the energy of the products lower than the reactants. So this is the opposite case. In order to make that happen, some energy had to come from the surroundings. Here I have it coming in as heat. Commonly happen to heat, altering the bonds, the potential energy interactions between them. Here, the enthalpy change then, final minus initial, a big number minus a small number, is a positive number. So the enthalpy change, this is an endothermic chemical reaction. Heat is absorbed. Very straightforward. And of course, if going from products to reactants for this, just doing the reverse reaction, you'd release that same amount of heat. So reversing the reaction, that heat would come out and you'd end up at the reactants. And this would be the exothermic process, releasing energy. You can measure the heat. And if you measure the heat in a calorimeter of a constant pressure process, that is the enthalpy change. That's handy. You can get a thermodynamic function by measuring in the lab an experimental parameter that's relatively easy to measure. The heat evolved or the heat absorbed when a reaction occurs. Okay, I don't think any of that's very surprising to you guys. What we're going to do, though, is we have to start to decide where that zero is going to be. Remember, we could choose zero anywhere with our potential energies. We have to start deciding, since there's all kinds of chemicals, where is zero going to be? It's kind of hard. First, we'll define a standard state. If you're going to compare apples to oranges, methane to water, at least have everybody in the standard state so you can start to make comparisons. And what we do is we define the standard state. So if you're going to have a chemical reaction, the standard state is put everything, if it's in solution, put everything at 1 mole per liter. So I use these little brackets, the concentration of A, these square brackets. 1 molar, capital M, 1 mole per liter. So if everything at products and reactants, everything is at 1 molar, then that's the standard state of a liquid phase reaction. If you have a gas, it has to be present on the products and reactant side at 1 atmosphere of pressure. And pure liquids and solids simply have to be present as pure liquids and solids. So if you can arrange the products and the reactants, it's very artificial. If everything is at 1 molar on 1 atmosphere, then that's very artificial state, but we need to go zero somewhere. We need a reference somewhere. So that's where we're going to go, everybody in standard state. So if you look at a standard state reaction, it's not the reaction that you'd normally do, pour it in solution and let it go, where all the concentrations are willy-nilly. Okay? If we want to compare that reaction to another reaction, then we better say, well, let's make sure everybody's on equal footing. Let's have 1 molar of everything and 1 atmosphere of everything. Okay? Let's do it. Boiling water hazard. The enthalpy for this reaction is plus 44 kilojoules per mole, going from liquid water to gaseous water, which then is the most hazardous at 100 degrees, water at 100 degrees, steam at 100 degrees, a combination of water and steam at 100 degrees. Which would you least want to come in contact with? Think about that for a second. We'll take a vote. I'll go talk to another. So in my Zoom room, there's a question, what do you mean water steam? It's just both of them. If both of them come in contact with your skin at the same time. Okay, I'm back. Let's see what you guys are thinking. Many now say steam, 2/3. If you guys can see that, say steam. I agree with the steams. Why is that? Um, well, in my group, we had a good discussion. One person heroically watching live from China at midnight. Awesome. Thank you for choosing Chem 1A for your uh, chemistry educational needs. He's going to the University of Michigan. How about that? I went to Michigan State. What I lost my train of thought. What were we talking about? So excited somebody was watching from China in real time. The steam is the more dangerous. They're all at 100 degrees C. So the temperature of the water and the steam are the same. And remember, when you changed the phase, it was isothermal. You went from liquid water to steam, both at 100 degrees. So why is the steam more dangerous if it's both at 100 degrees C? Well, now we know that what you do, water at 100 degrees C, that's going to burn you. Don't put your hand in that. It's 100 degrees C water, and it will transfer heat energy to you based on your heat capacity and its heat capacity. and it will happen relatively fast, especially if there's a lot of it. However, to make the steam, you had to add all this more energy to the system. So this is energetically more dangerous than this. You touch steam and it condenses on your hand and releases 44 kilojoules per mole. And then you still have boiling water on your hand. That's going to burn you too. Okay? So don't come in contact with steam if you can avoid it. Much, much more dangerous. We'll talk about this one together. Here we're going to isomerize propanol. So we're going to go from propanol that has these bonds. We haven't really even, I'm assuming you kind of have seen a molecular structure written out. We haven't formally said. These lines represent the bonds between the atoms. Those are the interactions where the potential energy has to be added to affect those. So when propanol isomerizes to isopropanol, and when we say isomerization, that means the same chemical formula, poopity poop, I gotta watch my touching of the board, the same chemical formula. So CH3O678, excuse me, C3H8O is the same formula you have over here. But their structures are different. They're isomers of each other. Same chemical formula, different structure. And I'm telling you that going from one to the other is endothermic. That takes energy to go from one to the other. That's what endothermic means. So which burns cooler? If you ignite propanol or isopropanol, which has the hotter flame? That's an interesting concept too. A lot of times we'll look at a flame and say, oh, that's a flame. It's hot. They're all about the same. They're not. It's what's burning is releasing the energy. So it matters what fuel is burning. A lot of these ignition reactions happen at the same rate. So if you have more capacity to release per mole, then you can have the reaction occurring at the same rate, but more energy coming out because you have a higher energy release. But it's actually easy to plot. If propanol is here on the energy scale, we haven't defined exactly where 0 is yet on the energy scale, but let's just slap propanol there. And one of the reason state functions are nice is only finest minus initial matters, and 0 can be anywhere, and the math is still the same. So two great properties of state functions. So regardless of where 0 is, if propanol is here on the energy scale, then isopropanol, then propanol, when you burn it, I hope you understand all combustion reactions are exothermic. That's something I think you intuitively know, and all of them lead to carbon dioxide and water. So if you burn propanol, you get 3 moles of carbon dioxide and 4 moles of water. Isopropanol, exactly the same, because it's got the same number of carbons and oxygens and hydrogens, just arranged differently. But if you isomerize the propanol to the isopropanol, that was endothermic. You had to go up in energy. But final state is exactly the same, 3 moles of carbon dioxide and 4 moles of water. So you burn the isopropanol and it burns hotter, releases more energy per mole than the propanol. Kind of cool. Do we have a demo for that? No. Okay, so now let's get right to where exactly the 0 is. We're going to get to standard states, but the full 0 on our enthalpy scale, we're going to, since we're talking about just chemicals, just every possible chemical combination, what we do is set 0 as the elements in their standard states. So the elements on the periodic table, in their standard states, 1 molar if if you have them in a solution. Most of them, you'll have a pure solid, pure liquid, or pure gas. So if it's a pure gas, it's 1 atmosphere. So the pure liquids are solids, and the gases at 1 atmosphere. That's level playing field. We're calling all of those 0. Those all have 0 enthalpy. Now we can compare everything else, every combination of the elements, to that 0. All the compounds, every time you mix something together and make a compound out of the elements, its enthalpy, where you put it on the scale, is relative to this 0, as long as it's in its standard state. So here's a bunch of elements in their standard state. Hydrogen gas, and notice that's not atomic elemental hydrogen. It's the element in its standard state, how you would find it in nature. Hydrogen gas, oxygen gas. Solid carbon graphite, not diamond. Nitrogen gas, iron solid metal. A couple examples. Now, you know, if you form now compounds from those, some may require energy to form, some may release energy to form. So we call these enthalpies of formation. And enthalpies of formation can be either endothermic or exothermic. It can either be a release of energy to form the compounds, or it takes energy to form the compounds. So we're starting to get to a point where we see a lot of thermodynamics taking shape. In general, we have this idea that energy, there are these wells and hills of energy. And in general, low energy is favored by the universe. If all else being equal, lower energies are better than higher energies. So if the universe goes on forever, everything's going to end up at the same energy. And all the low energies will be favored as we get there. So that points out kind of right away that many compounds are more favorable, they're lower energy than the elements in their standard states. And we kind of know that because in a broad sense, there are a lot of compounds out there, and they're stable sitting on the table, and they don't spontaneously change back into the elements in their standard states. So they're in some potential low enthalpy well, and they're sitting there. It would take energy to get them out. So here are some compounds. Water. To make a mole of water from hydrogen and oxygen gas, you would release 242 how am I doing this? Kilojoules per mole. Here, I'm making the elements from the atomic elements from the elements in their standard state. Remember, these are not the atomic elements. These are how you would find them in nature. So you can already see those enthalpies that we've been talking about. If you're going to make liquid water from the elements in their standard state, it would release more energy than the gas. And you could have written that because you know the arrangement of these two already. That's why kind of the 0 doesn't matter, because really we were just talking about this. It didn't matter when we were doing that discussion that 0 was up here. We just cared about that change there. Delta H was the important thing. And of course, if you vaporize it, you have to absorb that 75 kilojoules per mole. Here's forming carbon dioxide. In a sense, carbon dioxide is a lower energy molecule. Sometimes you would call that more stable. I try not to use the word stable. It's stable over time, but time is not a thermodynamic variable. It's in a lower energy state. That combination of atoms and molecules, atoms into a molecule, is a lower energy combination than this one. So let me ask you then, let me just ask you quick. Let's just turn it on quick. Just gut feeling, which is the stronger bond? O2, N2, or are they about the same? So I got that started, so you got that. Let's just go back to the picture. Which is the stronger bond, between two oxygens or between two carbons? And just take a shot. We'll just, this is just your personal thought. We won't discuss it too much. So let's get 90 voters or so, and we'll see what you're thinking. Okay, push a button if you haven't. Just your gut thought. We'll see what you're thinking. It looks like B is twice as popular as A. And what are those B people thinking? Those B people are thinking, well, I'm looking here, and here's nitrogen gaseous atoms, here's oxygen gaseous atoms. So if I go from nitrogen gas or oxygen gas, which is the element in their standard states, I have to put energy in. And that should make sense to you. If I have a molecule and I want to rip it into atoms, lots of potential energy has to be added to the system. Anytime you break a bond, it requires energy. If you take nothing else home from Chem 1, take home the fact that breaking bonds always requires energy. They're held together. That's why they're there. If it released energy, then it would probably be happening all the time. So you have to pull them apart. So pulling, I agree with the nitrogens, pulling apart the oxygen atoms is easier energetically. It doesn't require as much energy to pull apart two nitrogens. So we call that a stronger bond. Harder to pull apart, more tightly held together, greater attraction. And in fact, we're going to see that, in fact, that's a triple bond and the oxygen is a double bond. Now, atomizing carbon, you have to break all kinds of bonds. We'll talk about that too, but a mole for each of these, the reason they're all single bonds in carbon, but the arrangement of the bonds in the solid is such that it takes a tremendous amount of energy to atomize the solid carbon over atomizing the gases. Okay, I'll go through this because we're a little behind, and I'd like to run through a few more concepts, super important concepts. So let's focus. Thermodynamic cycle. Final minus initial is how you measure changes. So as long as final and initial are the same, the change is the same no matter how you got there. Okay, so you could go and stop a bunch of places, and as long as final and initial are the same, the enthalpy change is the same. That means you can add up the individual enthalpy changes, and it should equal the final enthalpy change. So that's true for all state functions. So if you go around a circle, let's do it. You start at state 1, you go to state 2, and then to state 3, and then back to state 1. So you come back to the final state, then the energy change is 0 because your initial and final states are the same. So this path, H1, H2, H3, delta H3, has 0 enthalpy. So thermodynamic cycle, where you start and stop at the same state, 0 change in that state function, 0 change in enthalpy. We're going to leverage that now to make use of our 0 in enthalpy. So let's say the reaction 3, state 2 and 3 is our reaction. A and B going to C and D. Okay, A moles of A, B moles of B, going to C moles of C, and D moles of D. That's our chemical reaction. It would be interesting to know what that enthalpy is. We could go to the lab and measure it. but it'd be interesting to know what it was. Maybe some of you are going to anticipate what I'm going to do. Why don't we make state 1 the elements in their standard states, so that everybody's on equal playing field? Then this reaction here is the enthalpy of formation of A moles of A and B moles of B. And this is the reverse, the opposite sign of the enthalpy of formation of C moles of C and D moles of D. I'll just write that down there. This enthalpy I can get by taking the enthalpies of formation of the compounds, and this one I can get by taking the enthalpies of the formation of the compounds. So I'm going to write it as a sum here. This symbol, capital sigma, means add up all the enthalpies of formation of the reactants, keep the stoichiometric coefficients. So multiply. Remember, energy is extensive. It matters on how many moles there are there. And do the same thing here. Calculate the enthalpies of formation of all the products. Take the opposite sign because it's going in the opposite direction of what we're calling enthalpy of formation. And then what is delta H2? Well, delta H2 is what we want to know. Let's throw those two to the other side. So delta H2, which is the enthalpy of this chemical reaction, is the heat of formation of the products minus the heat of formations of the reactants. Super cool. That means we don't have to do every reaction. In fact, the reactions that we should measure in the laboratory are making the compounds from the elements in their standard states, measure those heats of formation, and then you can use those heats of formation for any chemical reaction between any of those compounds. So what you need, what you want, is a table of enthalpies of formation. Again, this is one of those places where you might see somebody say heats of formation. And that's not horrible. It is a heat that's released. That's how we measure them in the lab. But it's an energy change. You can't plot a heat on those graphs that we're using. It's an enthalpy of formation. But if you're using a textbook that uses heat, it's the same thing. One person in one of my groups said for boiling of water, there was the latent heat of vaporization. Latent means it's just laying around there, and they call it a heat. Latent heat of vaporization. It is that 75 kilojoules per mole, but that's old terminology. We don't say latent heat of vaporization anymore. We say enthalpy of vaporization. The liquid can't have a heat. It can only have an energy. Okay? So here's a general table. We've seen some of these already. We wrote these heats of formation out for those molecules. Here's some additional ones. Here's ethanol liquid. Here's glucose, C6H12O6. Iron oxide, aluminum oxide, and just a few compounds that would be made out of the elements in their standard state. So solid metal aluminum, solid metal iron, carbon solid, nitrogen, oxygen, and hydrogen gas at 1 atmosphere of pressure. And I would have to form these things as pure liquids and solids. And if it's a gas, I'd have to form it at 1 atmosphere of pressure for these values to apply. So what is the reaction, the heat of enthalpy of reaction? How much heat is absorbed or evolved? What's the enthalpy change going from iron, rusting it to iron oxide? So take iron metal, expose it to oxygen over time, it goes to iron oxide. What number is that? Think about that. Let's just go through this one. So what do? Well, I can do heats of formation of the products minus heats of formation of the reactants with a table like this. Iron oxide, we gave you 824. That's the heat of formation. of iron oxide. And this reaction is the heat of formation of iron oxide. These are the elements in their standard states making iron oxide, rusting metal. And indeed, you release that 824 kilojoules per mole of iron oxide that you make. And that is kind of why iron, if you let it sit out, eventually rusts, because if you have iron and oxygen here, they're higher in energy than iron and oxide molecules. So over time, they go down the hill and form the rust. We can form it very fast. Oh, come on. Let's watch Lonnie do it. And instead of using gaseous oxygen, let's have Lonnie use liquid oxygen. So here's liquid oxygen. How's the glare on the screen? Should I lower the brightness? He's going to take liquid oxygen, and liquid oxygen, I don't know if you can see this, but liquid oxygen has a beautiful blue color to it. Hard to see. You can see in front of it, that's lovely blue. We'll learn kind of why that's a blue color. It's actually crazy complicated, but we'll learn kind of why that's blue. So here's a piece of iron, some steel wool, and he's going to put it in there. We know it's downhill. He'll start it burning, and then, oh my gosh, you make rust very fast. So so much energy released. Oh, slow-mo. Thank you, Lonnie. Can't do that live. So there is a slow-mo replay. The beaker shatters because the heat is released so fast if you do it that way. So let's just save the next one for next time. Of office hours right now, 9:30 on Thursdays. So I'm just gonna hang right here, and we'll keep the live stream going, because anyone can replay the office hours if they'd like. And you may, Andrew, can we take everyone out of their individual rooms, put them in one room? And if you have questions, you can ask them live over the Zoom. We don't have to put your face up or anything, but you can talk. Or you can enter them in the chat, the live stream chat, and we'll listen to them there, or we'll get them there. So any comments, questions? Think about it just a second. I need some water. I'll be right back. Okay, I'm back. Are there any questions coming in particular? None in the chat. Oh, okay, yeah. Administrative stuff. There's some administrative things coming in the Zoom. Of course, everything you need to know is on the webpage. So no science? I can't believe that I'm being that so clear that there's no confusion. Go ahead. Is there? Lucille asks, is a question, can you assume a reaction is isothermal, adiabatic, exothermic, or endothermic even? The first two, isothermal and adiabatic, are pathways, how you got from one place to another. Exothermic and endothermic are the energy changes. They're the same regardless of how you got from one to the other. So the first answer to your question, Lucille, is if you're calculating an enthalpy of a chemical reaction, don't matter whether it happened. The path does not matter. All that matters in the chemical reaction is you start with products, reactants in their standard states, and you end with products in their standard states. Then you can calculate an enthalpy, or you can measure it in the lab. If you measure it in the lab, most things happen adiabatically. We'll do them in a calorimeter maybe, but they'll happen adiabatically just because they happen fast. So if they happen fast, they release all their energy. Heat takes a while to transfer. All reactions, if you wait long enough, are isothermal, because every reaction, if it goes from products to reactants, even if energy is released, the products eventually become the same temperature as the reactants started if you started everything at room temperature. Will I ask you? No, I won't. I'll tell you if I want you to think about it isothermally or adiabatically. Sophia asks, can we just go through this? I don't know if I do on the or not. The answer might be not. I'll do it then, chalk talk wise. Yeah, that's all I do. So if you were going to do it, so let's do this. Let's go back to our table. There's our table. Let's grab it. Let's put it on the chalkboard. We'll change the chalkboard to dark background. And oh, there's already something on the chalkboard. Well, this other thing, let's get rid of. Oh, there. Goodbye. Oh, there. This thing, let's just put up there. So the question was, can we just go through the process? For this one, the process becomes kind of trivial because some of the values are 0. But if I take iron, I'll go a little fatter pen. If I take iron in the solid standard state, and I add oxygen gas, 1 atmosphere at standard state, and I make, I make Fe2O3 solid. That's the compound rust. How do I go about calculating what's going on there? Well, I can just go straight to my formula. That is the enthalpy change for any reaction standard state. I didn't emphasize it enough. That little degree sign there means everything in its standard state. Remind me to say that to everyone next time. I'll try to remember. So what's the standard state enthalpy change? The standard state enthalpy change is not what Lonnie did. His products and reactants weren't all, there wasn't 1 atmosphere of oxygen gas, and there wasn't, but iron solid was there, and solid rust appeared at the end. So he used oxygen liquid, different. you can still get an idea, even if everything doesn't end up in standard states, you can get an idea what's happening. So I'm going to take the enthalpies of formation of all the products, and I'm going to subtract away the enthalpies, standard enthalpies of formation of all the reactants, and then I go to the table and I look them up. So let's look at our table. All of the elements in their standard state, their enthalpies of formation are 0. That's our 0 point. That's an element in standard state. That's an element in standard state. They're also the reactants. So this is 0. Enthalpies of formation of all the reactants added up. Where's the iron oxide? There it is. The iron oxide solid, its enthalpy of formation minus 824 kilojoules per mole formed. So this number, there's only one of them, is minus 824 kilojoules per mole. Okay, add those two up. It's trivial. As I said, one of these, this time it's trivial. If there were a bunch of reactants over there that you had to get heats of formation for, it would be a little more complicated. But at least the math is easy. Minus 824. Okay, you like that, Sophia? Give us a thumbs up in the chat, or ask for more clarification. Good question. Other things?
Amanda asks, in the handout for lecture 3, it says, quote, it takes time for heat to flow. So if you do work quickly, you will always get the adiabatic result first. Once the heat flows, the overall process can become isothermal. Quote, I am confused how an adiabatic process can become isothermal since there is no time for heat flow.
Good question from what was her name?
Amanda.
Amanda says, quote, she read something from the notes attached to the slides, and it said something to the effect of, if you do a chemical reaction and it happens fast, you get adiabatic by default. That pathway is adiabatic because it takes time for heat to flow. So energy can be released, but heat flows, so it's adiabatic, and the system can end up at a higher temperature because the heat is still all in the system. So if you wait, that heat will flow out to the surroundings. There's no way to stop it. There are no perfect insulators. Some very good ones, but it's hard to get perfect insulation. An absolutely perfect vacuum might do it. But if you wait, that heat eventually goes to the surroundings. So if you wait a long time, then all reactions are isothermal. So it's kind of like this. I think I can erase the entire board. It's like this. You have reactants going to products, and let's say it's exothermic. So here's our energy scale. The reactants are here. The products are here. That releases a bunch of energy. And if you do that fast, that energy is released, and it could be trapped in the system. Remember when we did it, the gas expanded adiabatically, and it expanded so fast that the heat was there was heat trapped. In this case, the energy of the system, it was endothermic. We're absorbing energy. Excuse me. We were doing work. We were using some of our energy. So it cooled the system. That was the adiabatic process. The heat stayed in the system. But if you wait long enough, then the frozen carbon dioxide turns back to gaseous carbon dioxide at the same temperature it was in the cylinder. So we went from products to reactants, or one state to another, and did it fast. So we call it adiabatic. Heat's trapped in the system. You wait, and it's transferred to the surroundings, and then they're at the process is formally isothermal because we went from one to the other. But you're saying, okay, that sounds super complicated. Everything we do in thermodynamics is isothermal in this class. I'll tell you if I want you to think about the fast adiabatic case just as a thought experiment. But if you want to take heats of formation of products minus heats of formation of reactants, these are all not only taken at standard state, 1 molar or 1 atmosphere or pure solids and metals, they're also taken at the same temperature. So you have to wait. If the reaction happens, you have to wait till the products come back to the same temperature, room temperature, before that number applies, before that enthalpy, because some of the enthalpy is trapped in the energy of heating up the products. You have to wait till that is released into the surroundings before your enthalpy is correct. Does that help? All right, wonderful. Other things?
Yes. So Grace asked, on the homework assignment, there was a question regarding relative mass on the mass spectrum. In general, what properties can be inferred from the peak of any number of the mass? I'm guessing just the mass.
So that was Grace asking, what information is contained in a mass spectrum? I might not have made that clear enough. If you have a mass spectrum, you could essentially, you're plotting the number of particles versus the mass of the particles. So the height of the peak is the number of particles. In general, we don't care how many exactly. We don't care the magnitude of this scale. If there's another peak, though, the relative heights are the relative numbers of particles. So that's the information you get. So you get a mass number. And if you do formal mass spectrometry, you can calibrate it. So these aren't even relative masses. They're exact masses. But of course, if you have exact masses, then you calculate the relative mass by dividing one into the other. But you'll get exact mass and relative amount. About it? Coming in?
So I may pronounce their name wrong. Asked, is kinetic energy from the motion of the atoms/molecules or the motion of their electrons?
Oh my, what a wonderful question. So we're having trouble pronouncing your name, Mihili, or I can't read it. There's a question. Is kinetic energy the energy of the atoms and molecules in the system? Do we include the kinetic energies of the electrons? Formally, no, you don't include the kinetic energies of the electrons. Their kinetic energies are changing like crazy because if you're breaking and forming bonds, and that's the nature of the reaction. However, they also have these ridiculously small masses, and they all settle back down to about the same kinds of kinetic energies they have. So since it's a small component and the difference is small, the kinetic energies are the things, think about the kinetic energies as the things that you could measure with a thermometer. And I guess, I'm sorry. So I kind of assume, and this is bad, a lot of people do this, they assume that you have some intuition. When you put a thermometer in a sample, you're measuring kinetic energy. And the electrons aren't knocking into the kinetic energy of the electrons don't matter. The electrons are actually what's bouncing into it, but they're bouncing into it all at once. And they're making the thermometer heat up or cool off. Their individual motions don't matter. It's the motion of the entire particle, the entire atom or molecule hitting the thermometer that matters. Great question. I'm glad you're thinking about the kinetic energies of the electrons. Awesome. Other things?
Yes. So Lucille has another question. In reaction profiles, there is an increase in energy before the formation of products, even if the reaction is exothermic. You said the universe tends towards lower energy states. So how would the reactants spontaneously gain sufficient energy to overcome the initial increase in energy?
Goodness.
Wouldn't they be more stable, not reacting, since they are lower energy than the intermediate state?
Okay. Great question from Lucille. Lucille saying, when you draw the energy profile, so that reaction coordinate business, I was doing this. I was doing energy here, and then I was kind of plotting, and this isn't even really time. This is just reaction progress. So, and if you drew, and Lucille was kind of pointing at this thing, here's this reaction, reactants, products. We know now that this reaction is endothermic. Okay, I absorbed energy to get from the reactants to the products. But what about this hill in the middle? How does any reaction ever spontaneously get enough energy to go from here to here? And we're going to talk about it in some detail. But let's say for now, you've seen that often you have to give them the energy. You have to heat up reactions to get them to go, or a flame. So getting over this hill, you're exactly right. What we're saying, that products and reactants can become trapped as products and reactants because, compounds can become trapped in these low energy situations. It is because of these hills between the products and reactants that prevent them from changing over time. So if this hill is high, then if it's products, it will stay as those products. It's hard to get out. If it's reactants, it's even harder to get out. So let's say over time, some tiny percentage of the molecules have enough energy to get over. We'll learn that in any group of molecules, the statistics says that there's some that have tremendous kinetic energies. And let's say just those tiny, it's that tiny 0.0001% react over time. Well, that means here in the products, some tiny percentage would go over here if you wait long enough. Same thing. The reactants, some tiny percentage would go that way. But if you wait over time, the going this way is easier, lower energy. So if they're at the same temperature, then reactants are going to build up because it's harder to leave the reactant well than the product well. That's why we call these more stable over time. So, short answer, yes, that barrier is there. You got to give it that energy to get there in general. But this stability still reflects the fact that over time, that this is the more stable compound. You'd see it after 100 billion years, I guess, over this one, if the universe has its say in the matter, thermodynamics. Other things? Oh, well, you're welcome, guys, for that. Hopefully we'll meet in person if you guys are around. Certainly try to come by, say hi. Anything else coming in? All right, wonderful, guys. We'll take a break here then, and see you Monday.